Experiment 9 is on calorimetry, specific heat. So this covers chapter 6 in your lecture. So the objectives of experiment 9, there are three objectives for experiment 9. The first one is to measure the enthalpy of three chemical reaction. To use Hess law to verify that the enthalpy change of the first two reactions can be used to deduce the enthalpy of the third reaction, and then to measure specific heat of certain metals. In this experiment, we're going to look into the concept of enthalpy. Okay? So enthalpy is the amount of heat liberated or absorbed as reactants change to the products, and usually it is represented by the delta H sign. We could say the enthalpy would be exothermic for reactions that lost heat to the surroundings, and you have a negative delta H. And enthalpy would be endothermic for reaction that absorb heat from the surroundings, wherein your delta H is positive. So for instance here, okay, the reaction of hydrogen with oxygen to produce water is an exothermic process. Now, calorimeter is the one device that is used in the laboratory to measure the loss or gain of heat energy, and we will have our own homemade calorimeter, or the so-called coffee cup calorimeter. Okay, why coffee cup? Because it's made up of styrofoam cups. Okay, in this experiment we're going to use calorimeter, and in the first part of the experiment we're going to determine the heat capacity of the calorimeter that we have. Okay, so we're using our styrofoam cups. That's why we need to determine its heat capacity. So this is done by mixing ice cold water with hot water. So we assume that the heat loss by the hot water warms both the cold water and the calorimeter, and that there is no heat loss to the surroundings in the calorimeter. So if we're going to sum it up, we could say this is what Q of the hot water is just equals to the Q of the cold water plus the Q from the calorimeter. So the way that we look at this here, so this is the heat released by the hot water, and that is equals to the heat that is gained by the cold water and the calorimeter. So if we're going to break them down, okay, so the Q that was released by the hot water is just equals to the mass of the hot water times specific heat of the hot water times change in temperature. Okay? So what is the initial temperature before you add the of the hot water, and then what's the final temperature after it became cold? Now Q cold, on the other hand, that is the heat that was gained by the cold water. It's the same as the mass, okay, of the cold water times the specific heat times the change in the temperature. Now the Q-cal, the heat gained by the calorimeter, we could say it as equals to Cp. So that is the heat capacity times delta T. So if you're going to look at this, this is just what we have. Now what we're going to do, if we're going to keep all temperature changes into positive quantities, so we can get the heat capacity as equals to hot water minus cold water over the rise in temperature. And this is just, we could say, getting the heat capacity. Okay? In the second part of the experiment, we're going to do a series of mixing different reagents and determine the heat or indirectly the heat of reaction. So the way that we do it is the heat released by an exothermic reaction is equals to the enthalpy of the reaction, but opposite inside. So we could say Q reaction is just equals to the enthalpy change. And the way that we're going to look at this, so this is in terms of the heat in the calorimeter plus the heat capacity of the calorimeter. So knowing the heat capacity of the calorimeter, which we determine in the first part, and measuring the mass of the calorimeter content and the temperature change allow us to calculate heat of reaction and enthalpy. Okay? So we will have a series of reaction like this one. We have acetic acid reacting with sodium hydroxide to produce this material, and then we have 2 moles of sodium acetate reacting with sulfuric acid to produce this material. And if we're going to add them all, where this Hess law come in, because if we're going to look at this Hess law, what it do is just, it pertains to the heat summation. Okay, so when you add reaction, okay, the total enthalpy or the enthalpy of the new reaction is just equals to the sum of the enthalpy of the reactions that you added. So the way that you're going to do the reaction here is, in the end, okay, you will just get the delta H of the third reaction here by adding the 2. So if you're going to look at this, there's 2 here, so we could say 2 delta H1, add it with delta H2. Now you may ask, why do we have to make it 2? Because if you're going to look at here, you need this to have 2 to cancel out some of the materials that you have there. So this one is cancelled out, this one is cancelled out. What else is cancelled out? Okay, so the one that remains is the sum of the reaction. Now the last part of the experiment is the specific heat of a metal can be measured also using a calorimeter. So what you're going to do, you know, a weight quantity of metal, you heat it to a known temperature and then pour it in the calorimeter containing a known mass of water at a known temperature. And the water and the calorimeter would absorb the heat from the metal, okay? And this is just similar to what we have done earlier, or maybe in the lecture part, wherein we could say Q is just equals to the mass times specific heat delta T. So the one that we trying to determine here is this value. Okay? For determining the heat capacity of the calorimeter, you're going to place 50 ml of ice cold water in a styrofoam, and then you place the thermistor in the ice water and collect the time versus temperature data for about 2 minutes. While doing it, you heat some water in a beaker on a hot plate. You measure 50 ml of the hot water and pour it into another styrofoam cup and measure the exact temperature. And then you're going to pour the hot water into the cold water. You swirl it gently to mix the contents of the calorimeter, cover and allow the data collection to go for another 2 to 3 minutes or until the temperature stabilizes. Record the final temperature. Now for the second part of the experiment, we're going to mix several reagents and determine the heat of reaction. First thing that you're going to do is measure 50 ml of 2 molar acetic acid solution and place it in the calorimeter. You cover the calorimeter and place the thermistor in its position in the lid and collect the temperature for 2 to 4 minutes. Now, measure 50 ml of 2 molar sodium hydroxide into a grad cylinder and then add the sodium hydroxide and place the lid over the calorimeter without interrupting the data collection. The reaction will be monitored for another 5 minutes. Record the temperature. And then you're going to repeat it with other reagents. wash the colorimeter with tap water and then dry it. You can use a paper towel to dry it. And then you repeat the experiment, this time with 50 ml of sodium acetate added with 50 ml of 1 molar sulfuric acid. And then you wash the colorimeter and dry it, and then repeat the experiment again, this time with 50 ml of 2 molar NaOH and 50 ml of 1 molar sulfuric acid. For the specific heat of metal, weigh around 10 to 20 grams of the metal shot and gently transfer it to a 25 ml test tube. So you climb the test tube containing the metal in a water bath and boil for about 5 to 10 minutes. So at this time, the temperature would be around 100 degrees Celsius. So while you're doing that, you measure 50 ml of tap water and place it in the calorimeter. Okay? You measure the initial temperature by placing the thermistor in the calorimeter, and then use the clamp to remove the test tube that contains the metal from the boiling water bath and pour the heated metal into the calorimeter. Okay? So make sure you stir the mixture gently. Okay, so you cover the calorimeter when you pour the heated metal. You monitor. You're going to stir it gently, and continue to monitor the changes in the temperature. Okay, and then from the data with respect to the change in the temperature, you should be able to calculate the specific heat of the metal and identify the metal.